You will note the broadcast is now starting. All attendees are in listen-only mode.
Hello, and welcome to this online lecture. My name is Patty Kokish, and I teach various math classes in the Northwest region, both in person and online. Today, I'm going to be going through a midterm exam review for Math 200. I believe you have to take your midterm sometime this week, so this would be a great thing to watch while you're studying. So I'm going to start with chapter 1. We're going to hopefully touch on all the chapters depending on what we have time for. But chapter 1 was all about data collection. So the first thing I want to talk about is the difference between a population, a sample, and an individual. And we're going to get into this into a little more detail in just a little bit. But what you first need to know is that the entire group of individuals that you're studying is called the population. An individual is just someone that is a member of the population being studied, and then a sample is a subset of the population. So typically when we're doing some kind of a study, we cannot possibly ask everyone in the population for their opinion or whatever it may be. So what we do is we take a sample, which is a subset of the population, and we ask them that question, and then we use different inferential methods to get back to our population. So I want to talk about the process of statistics. This is something really important, and hopefully this kind of brings together some of the things that you've done in this class so far, and then also gives you a preview of some of the things that are ahead. So the first thing that we always do is we want to identify the research objective. So a researcher must first determine the question or questions that he or she wants answered. The questions have to be fairly detailed so that we can identify the population and come up with the correct way of figuring out how to answer our question. And the second step would be to collect the data that's needed. There are a couple things you have to keep in mind, though. First of all, gaining access to the entire population is often really difficult and very expensive and time-consuming. So when we're conducting research, we typically look at a sample, like I already talked about. Collection of data step is vital to the statistical process, because if data is not collected correctly, then the conclusions that we draw can just be meaningless. So it's really important to properly collect the data. The third thing we do is once we actually have our data, we want to describe it. So we obtain various descriptive statistics. Those allow the researcher to obtain an overview of the data. It can start to provide some insight as to the type of statistical methods that the researcher should use to further analyze the data. And all of that was detailed in chapters 2 through 4. The next thing we do is actually perform some inference. So we want to apply appropriate techniques that we decided on to extend the results obtained from the sample back to the population. And we also always want to report some level of reliability. So we're not always 100% correct, but we try to quantify that somehow. So we discussed techniques for measuring reliability in chapters 5 through 8, and then some inferential techniques in 9 through 15, which we haven't gotten to yet. There are two types of variables that we're going to talk about. We have qualitative or categorical variables. Those allow for classification of individuals based on some attribute or characteristic. So for example, like hair or eye color. And then there are quantitative variables as well. And those provide numerical measures of individuals. So you can do arithmetic operations on them, like add or subtract them. And you could have some kind of meaningful result. Whereas qualitative is something that is just a category. It's not numeric. So let's do these and distinguish between qualitative and quantitative variables. So we have a researcher who studied factors that affect the eating habits of adults in their mid-30s. And we want to classify each of the following variables considered in the study as either qualitative or quantitative. So if we think about nationality, that one's going to be qualitative. It's not a number, all right? It's going to be some kind of word that's going to describe your nationality. So that's going to be qualitative. Number of children, though, that's going to be quantitative because we can count it, okay? Household income, also quantitative. It's going to be a number. Level of education is going to be qualitative, unless we're talking about specific grade level. But if we're talking about level of education, typically you think of less than high school, some college, associates, bachelor's, master's, or PhD. Those would be maybe some levels of education that we can talk about. And then lastly, daily intake of whole grains measured in grams, that's going to be quantitative because that's going to be a number. Discrete variable is a specific type of quantitative variable that has either a finite number of possible values or a countable number of possible values. So what I say when I say the word countable is basically we could count. So 0, 1, 2, 3, and so on. So under the category of quantitative variables, we have discrete and continuous. Continuous variables are also a type of quantitative variable, and those have an infinite number of possible values. So it can take on any measure of desired accuracy. So we can't really count all of the variables all of the levels that a continuous variable takes on. So let's do this as well. This is the same study, and we want to decide if these variables are discrete or continuous. So when you talk about number of children, if you think about it, you can count that, right? You could count it as 0, 1, 2, 3, and so on. And so that's going to be discrete. If we're talking about household income, that's actually continuous because there are a lot of different incomes that we can have, and we can also measure them to kind of any desired accuracy. We could measure them to the penny or anything like that. If we're talking about daily intake of whole grains measured in grams per day, that is also going to be continuous because we could have like 1.25 grams, 1.6 grams, anything like that. So it depends how accurately we're measuring that. We also have different levels of measurement. So the first level of measurement is nominal. We say that a variable is at the nominal level if the values of the variable name, label, or categorize. And in addition to that, the naming scheme doesn't allow for any actual rank or order to be associated with them. Ordinal level of measurement has all of the same properties as nominal, except that the naming scheme allows for values to be arranged or ranked. So we have something maybe that's considered best and something that's considered the worst. That would be something that would be ordinal. A variable at the interval level still has the properties of the ordinal level of measurement, and the differences in the values of the variable have meaning. So a value of 0 at the interval level does not mean the absence of quantity. Arithmetic operations such as addition and subtraction, though, can be performed on the values for that variable. And if you have something at the ratio level of measurement, it's very similar to interval, except this time a value of 0 means the absence of quantity. Okay, so let's look at these. A study was conducted to assess school eating patterns in high schools in the US. The study analyzed the impact of vending machines and school policies on student food consumption. A total of 1,088 students in 20 schools were surveyed. School lunch and snacking patterns among high school students and the associations with school food environments and policies were kind of the main things they were trying to get at. So we want to determine the level of measurement for the following variables that were considered in this study. So number of snack and soft drink vending machines in the school is going to be ratio. If we go back to our definition, ratio is something where 0 actually means 0. So if they don't have any types of snacks or soft drinks, then that just means they don't have any. So 0 does in fact mean 0. B, whether or not the school has a closed campus policy during lunch. That's going to be nominal. Class rank, freshman, sophomore, junior, senior, that's going to be ordinal because it has some kind of associated order. And the number of days per week a student eats school lunch, that's going to be ratio as well. So a student could eat school lunch on 0 days all the way up to 5. So in both, there are a couple of studies I want to talk about. The goal of the research in the study is to determine if radio frequencies from cell phones increase the risk of contracting brain tumors. So whether or not brain cancer was contracted is actually the response variable, and the level of cell phone usage is going to be the explanatory variable. So in research, we oftentimes want to determine how varying the amount of the explanatory variable affects the value of the response variable. So the explanatory variable is what we change, and we're hoping or trying to prove that it affects the value of the response variable. So those are a couple of key terms to keep in mind. An observational study is one that just measures the value of response variable without attempting to influence the value in either the response, or explanatory variables. So basically what we're doing is we're just observing behavior of individuals without actually influencing the outcome of the study at all. But if a researcher assigns individuals in a study to a certain group, like a placebo group or a control group, and intentionally changes the values of the explanatory variable and then records the value of the response, then the researcher is conducting a designed experiment. So if you're just observing and not actually doing anything with the response or explanatory variables, then that's going to be an observational study. But if you're actually manipulating things and kind of planning out how it's going to work, that's going to be a designed experiment. Now, a census, I think you've probably all heard of this when you talk about the US Census. Basically, it's just a list of all individuals in a population along with certain characteristics of each individual. So, for example, for the US Census, you're asked for income and a lot of other kind of demographic and socioeconomic information. So that's only done every 10 years because censuses are very, very expensive, time-consuming, unless you have a really small population. So this is kind of a summary of some different types of sampling. I'm going to talk about a couple of them in a little more detail. But simple random sampling, what you see up top on the left, is basically we just have people that are kind of numbered, all spread apart. And what we do is we randomly select 3 of them, okay? And that would be our sample. So simple random sampling, person 2 is not any more likely than person 7 or 5 or 4 to be chosen. Stratified sampling, what we do is we take it and we put people into groups. So for example, you'll see out of our population, we've separated into male and female. And then within male, we select 2 people, and within female, we randomly select 2 people. So it's random sampling within the strata, but first we stratify our people. Systematic sampling is something where we have people in some type of random order, and then we sample maybe every 3rd person or something like that until we end up with the sample that we want. Cluster sampling would take like a big group of people and stick them into clusters first. And then instead of randomly selecting people out of the clusters, they randomly select clusters themselves. So a place where you often see this is when you're doing something like maybe you're trying to figure out some type of information or something about how people feel about a certain new thing that's going to be happening, like building a playground in a certain residential community. So what you would do is maybe you would cluster your entire city into blocks or block groups, something like that, and then you would select entire blocks or block groups to sample. The idea with this is when you're talking about geography, it makes sense to sample people who are close to one another because it is cheaper to hire someone to walk around and go door to door if they're only going in specific neighborhoods instead of randomly going all over the city. So that would be a good example of cluster sampling. I want to talk a little bit about systematic sampling, and this is for if you know your population size. So if you're trying to figure out how to do a systematic sample, what you first do is you determine your population size and you determine your sample size. And then what you do is you take the ratio of those 2 things. So you take your big N, which is your population size, and you divide by your little n, which is your sample size. And then you round down to the nearest integer. And that value is going to give you k. And then what you do is you randomly select a number between 1 and k. You call that number p, that's where you start. And then the sample is going to consist of the pth observation, so the very first one. And then to find your second observations, you take p plus k. And then to find your third observations, you do p plus 2k. So each time you're just adding k, and that gives you the next person that should be sampled. Okay, now I want to go through kind of an example here where we talk about some populations, treatments, response variables, so putting some of this stuff into real context. So the English department of a community college is considering adopting an online version of the freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half of the students receive the traditional course, and the other half is given an online version. At the end of the semester, both groups will be given a test to determine which performed better. So if we want to know who the experimental units are, That's going to be all of the students that are actually in the class. The population is going to be all students who enroll in this particular freshman English course. The treatments are either a traditional or an online instruction. Response variable is going to be the exam score. And then it asks, why can't this experiment be conducted with blinding? If you remember blind, that's when either the experimenter or the people who are in the experiment don't know what treatment they're getting. And in this case, it doesn't make any sense because both the students and the instructor are going to know which treatment they are receiving. So the student knows if they're in the online class or the traditional class, as does the instructor. So there would be no way to do this with blinding. Okay, I want to talk about chapter 2. In particular, I want to talk about pie charts. Basically, a pie chart is just going to be a circle that's divided into different sectors or sections. Each section is going to represent a different category of the data, and then the area of the section is proportional to the frequency of the category. So if we look at this example, we have marital status and we have frequencies. And so what we do is we basically just change it so that they're percentages. So in order to do that, we take 55.3 divided by whatever our total is when we add all of this up. And we get 25% never married, 58% married, 6% widowed, and 11% divorced. And then that creates our pie chart. You always want to use percentages in pie charts. It's a lot easier to read and understand. And then the whole thing should always add up to 100. Now, the first step in summarizing quantitative data, if you remember quantitative data, that's numbers, is to determine whether the data is discrete or continuous. If it's discrete and there aren't very many values of the variable, then the categories can just be the actual classes that you use. But if the data is discrete and there are many values, or if the data is continuous, then you need to create categories, which we call classes. So if we look at this data here, here we have data representing the number of available cars in a household based on a random sample of 50 households. We want to construct a frequency and a relative frequency distribution. So for this one, what we need to do is we need to actually define our categories. And if you look, it looks like we have values of 0 through 5. So those are the number of cars that we have. And then we just put tally marks to kind of indicate how many of each category we have. We change it to frequency and to relative frequency. 50 is your total if you add up the frequency column. So to get the relative frequency, you just do each frequency divided by the total. And again, the relative frequency should always add up to 1. So we create something called a histogram, which I'm just going to show you here. And basically what we do is we just put our categories along the x-axis, we put our frequency or our relative frequency along the y-axis, and then we just draw bars so that they are touching. And that gives us our histogram. I want to look at these histograms and talk about what the shape of the distribution looks like. For this first one on the left, you can see that this is uniform or symmetric. Now, there are a couple of things that can look symmetric, but this one in particular is uniform because it's just the same all the way across. If you look at this one looks pretty bell-shaped. It's also symmetric, but this one is a very different shape. This one has like a tail on the right, okay, so we call that skewed right. And this one has kind of a tail on the left, so we call that skewed left. Okay, in chapter 3, we talked about numerically summarizing data. So a couple of kind of key points here are that we have sort of 3 different main measures of central tendency. We have our mean, which is calculated just by adding up all of our observation and dividing by the number of numbers. And that's normally nice to use when you have symmetric data. We also have a median, which is where you arrange your order in ascending order, and then you find the observation that divides your data in half, so that you have half of the observations below and half of the observations above. And this is nice to use when you have data that is skewed left or skewed right. It is more resistant to outliers. And then mode is just the tally of the data that's the most frequent observation. And when to use, it just says when most frequent observation is desired measure of central tendency or the data is qualitative. Typically, you're either going to be using mean or median. If you have something that's symmetric, you're going to use mean. If you have something that's skewed, you would probably use median. Range is always just the highest number minus the lowest number. And then population standard deviation is basically what you do is you just take the square root of the sum of the squared deviations around the mean. So what you'll see here is it's typically denoted with this sigma. Okay, it's a Greek letter, and here's the actual formula here. So basically you just take your observations, subtract your mean, you square those deviations, and then you add them all together, divide by n minus 1, and take the square root. So this would give you the sample standard deviation, which is typically denoted with an S, whereas the population standard deviation is typically denoted with sigma. The other thing you'll notice is we're dividing by n minus 1. N minus 1 is called your degrees of freedom because for the first n minus 1 observations, they have freedom to be whatever value they want. But the last observation doesn't have any freedom at all. It's just forced to basically be the value that makes the sum of the deviations 0. So if you want to compute the sample standard deviation, you have a couple of options. The first would be to just use your formula, go ahead and solve this, and you should get 15.82. The other thing is, in this class, you are allowed to use a graphing calculator, which does a lot of nice things for you. So I'm using a TI-84 Plus, and all of them should be pretty similar. But if you go into Stat and then Edit, what you're going to see is you have some lists there. I normally just put all of my data in list 1 and then I just use it as need be. So you probably, if you already have data in there, you're going to have to delete it. So you just hit the delete key until you don't have any data left in there. And then what you do is you enter your data. So you put 5 in first and then hit enter, and then you have a 26 and a 36. So you hit enter after each of those. And then what you're going to do is you're going to go back to Stat, and then you're going to scroll over to where you see Calc. And then you want, so that stands for calculate, and then you want to calculate one var stats. So you hit number 1, you hit enter, and what it does is it gives you your mean, and it also gives you your sample standard deviation. So you should see S and then X there. That's for the sample standard deviation for your X, and what you actually get for that is 15.82. So your calculator does that for you as well. Okay, we can also find quartiles. The first step for finding quartiles is arranging your data in ascending order, determining the median, and then dividing the data into 2 halves. So you have the observations that are below the median, the observations that are above the median. And then the first quartile is just obtained by taking the median of the bottom half. And then the third quartile is obtained by taking the median of the top half. Now, the thing that I want to point out is that your calculator will actually do this for you as well. It's done the exact same way. So if you're still on that one var stats page where it gave you all that information, if you keep scrolling down, what you'll see is it gives you the quartiles. It gives you Q1, the median, Q3, and the maximum. Now, if you're asked for the interquartile range, all you have to do for that is take Q3 minus Q1. So if you know your third quartile and you know your first quartile, all you have to do is subtract. And this formula, along with most of the other formulas that I've already talked about, are on your formula sheet, which can be found on Blackboard. So it says summary, which measures to report. So if the shape of your distribution is symmetric, then you're going to be using your mean and your standard deviation. So those two things kind of go hand in hand. Chances are if you're looking at your mean, you're also going to talk about your standard deviation. But if you have a distribution where you have something that's skewed to the left or skewed to the right, then you're actually going to look at your median and your interquartile range as your measure of dispersion. And this is a more resistant measure. It would be the median and the interquartile range, meaning that if you add extreme values like outliers, it's not going to change your values as much as the mean or the standard deviation would change. We have something called a 5-number summary. This is important to know, and I don't think that it's laid out precise. Oh, it is on your formula sheet. I see it here. It's always just the minimum, which is your smallest number, Q1, M, which stands for median, Q3, and then maximum. And then if you'd like to draw a box plot, what you do is you create these lower and upper fences by taking Q1 minus 1.5 times your interquartile range, and you create an upper fence by doing Q3 plus 1.5 times the interquartile range. And those give you your lower and your upper fences. Those formulas are on your sheet as well under Chapter 3. And then you draw a number line that includes the maximum and minimum values, and then you insert vertical lines at Q1, the median, and Q3, and then you enclose all of those vertical lines in a box and label the lower and the upper fences, and then you draw lines. Those are called whiskers that kind of extend outside of your box. Any data values that are less than the lower fence or larger than the upper fence would be considered outliers, and we typically mark those with an asterisk. So if you look at, here's an example here, we have a minimum, Q1, median, Q3, and maximum. This is an example of a box plot where you can see we have data that's skewed right because it has a really long whisker on the right. This one here actually looks pretty symmetric. Okay, this looks pretty good. And this one over here on the right is actually skewed left because it has a really long whisker on the left. Okay, let's talk a little bit about probability. So there are a lot of things in this chapter 5 that talk about just all sorts of probability. So I kind of picked the more difficult ones that I think, the ones that are towards the end of the chapter, but it's really important that you know how to do all of the questions from this section, and in particular, some of the ones where you're reading data from a chart. So let's talk about disjoint events first. Another word for disjoint is mutually exclusive. Basically, if two events have no outcomes in common, they're considered mutually exclusive. And we have a nice addition rule for disjoint events. If E and F are disjoint or mutually exclusive, then the probability of E or F is just obtained by taking probability of E plus probability of F. And this is given on your formula sheet. But if we're not sure, this is kind of our general addition rule. So if you're not sure if they're disjoint or not, what you should do is you should add the probability of E and the probability of F, and then subtract any overlap that you have. Now, if you don't have any overlap, then it means that yes, they are in fact disjoint. But if you do have an overlap, you're going to have some number here. And that is going to be obtained just by looking at how many you have in the overlap. And you always need to subtract that so that it isn't double counted. So let's look at this example here. Suppose a pair of dice is thrown. Let E equal the first die is a 2, and F equal the sum of the dice is less than or equal to 5. And then what we want to find is the probability of E or F using our general addition rule. So the first thing we have to do is we need to figure out the probability of E. So we want to figure out the probability that the first die is a 2. So if we look at all of our outcomes, it looks like we have this whole row here. We have 1, 2, 3, 4, 5, 6 observations where the first number is a 2. So 6 out of our 36 rolls, and we can reduce that to 1 out of 6. Now if we want the probability of F, which means the sum of the dice is less than or equal to 5. That's going to be, let's see, we have these 4 observations here, and then we have 3 observations here, 2 observations here, and 1 observation here. So if we add all of that up, we get 10 out of 36, which can be reduced by dividing the numerator and the denominator by 2, so you get 5 out of 18. If you want the probability of E and F, we take everything that's in the overlap, and there are going to be 3 of those, and we divide by 36, and we get 1 out of 12. But if we want the probability of E or F, what we do is we take our 6 out of 36, our 10 out of 36, we add those two things together, and then we subtract that overlap, that 3 out of 36, so that we don't double count. And if we do that, we get 13 out of 36. Okay. According to the American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? So anytime you're seeing the word not, chances are you're doing something that illustrates the complement rule. So really what you need to do is you need to write down the probability that someone does own a dog and then subtract that from 1. So what we have here is just 1 minus 0.316, and we get 0.684. Okay, we also have something called independent events. So 2 events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events can be considered dependent if the occurrence of event E in a probability experiment does affect the probability of event F. So we have a nice multiplication rule for when we have independent events. Basically, if we want the probability of E and F, all we have to do is take the probability of E and multiply it by the probability of F if your events are independent. So let's say that the probability that a randomly selected female aged 60 years old will survive this year is 99.186, according to the National Vital Statistics Report. We want to know what is the probability that two randomly selected 60-year-old females will survive this year. These two things are independent events because one person surviving the year has nothing to do with the other. So all we have to do is just take 0.99186 and multiply that by 0.99186. And if we do that, we get 0.9838. Now, we also have conditional probability rules. So if E and F are any two events, then the probability of F occurring, given that E has occurred, is found by dividing the probability of E and F by the probability of E. Or you can think of it as dividing the number of outcomes that are in E and F divided by the number of outcomes that are just in E. So if we look at this, we have kind of a crosstab of very different regions of the country and their beliefs about God. So the first thing we want to answer is, what is the probability that a randomly selected adult American who lives in the East believes in God? So what we would do is we want to find the probability that someone believes in God given that they live in the East. So what we do is we look at the number who are in both categories. So they believe in God and they live in the East, which in our case is going to be 204. And then we divide that by everyone who lives in the East. And so if you think about that, that's going to be 204 plus 36 plus 15. So you get 0.8. So knowing that someone lives in the East, there's about an 80% chance that they believe in God. Okay, if we want probability that they live in the East given that they believe in God, this time it's the other way around. We're still looking at that same overlap, that 204, but this time we're saying we know that they believe in God. So we are just looking at this first column here instead of the first row. So if you add all of those up, you get, well, I don't know. It's not given here. 204 plus 212 plus 219 plus 152. If you add those all up and then divide 204 by that number, you should get 0.26. So if we know someone believes in God, there's about a 26% chance that they do live in the East. Okay, another example. In 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? So we want the probability of male given 20 to 24. So what we do is we take our overlap and we divide by the probability that they are 20 to 24. So our overlap is 0.166, or 16.6%. And we divide that by the probability that someone is 20 to 24, which in our case is 19.1, so 0.191. So if we divide those, we get around 86.9%. Okay, so we have this nice general multiplication rule here. Basically, the probability that two events E and F both occur can be found by taking probability of E and multiplying by the probability of F given E. So in other words, the probability of E and F is found by taking the probability of the event E occurring times the probability of event F occurring, given that the occurrence of event E has definitely happened. So let's look at this. Same thing here. In 2005, 19.1% of all murder victims were between 20 to 24. Same kind of setup. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? So what we want is we want the probability that they are male and 20 to 24. So what we do is we take the probability that they were 20 to 24 and multiply by the probability that they were male given that they're 20 to 24. So we multiply our 0.869 by our 0.191 and we get about 16.6%. Okay, let's move on to chapter 6. This is discrete probability distributions. So first thing we talked about was a random variable. It's a numerical measure of the outcome from a probability experiment. So we determine its value just by chance, and then random variables are normally denoted using a letter like X. We have discrete random variables, which either have a finite or countable number of values. The values of a discrete random variable can be plotted on a number line, so you could count them. We also have continuous random variables, which are uninterrupted if we plot them on a number line. We have a couple of rules. When we add everything up, it has to be 1, so all of the probabilities have to sum to 1, and then all of the individual probabilities have to be between 0 and 1. So if we look at this, we have a formula for our mean, and that is basically just all you have to do is you have to take x times the probability and then add everything up. So if we do that, we have 0 times 0.06 plus 1 times 0.58 plus 2 times 0.22. We do all of that and we get 1.49. So this gives you the average number of DVDs that a person rents from a video store. We also talked about binomial probability experiments. It's really important that you remember what makes something binomial. So there are a few things that have to be true. First of all, the experiment has to be performed a fixed number of times. Each repetition we refer to as a trial. The trials have to be independent, so it means that the outcome of one trial has absolutely nothing to do with the outcome of another trial. In addition, for each of the trials, there are 2 mutually exclusive or disjoint outcomes. So there's either a success or a failure. So it's nowhere in between. It always has to be either success or failure. And then the probability of success is fixed for each trial of the experiment. So we want to know which of the following are binomial experiments. So a player rolls a fair die 10 times. The number of sevens rolled is recorded. This one is in fact binomial. Here we have the 11 largest airlines. They had an on-time percentage of 84.7% in November of 2001, according to the Air Travel Consumer Report. And in order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 of them that were not on time. This one is not going to be binomial because it's not a fixed number of trials. So we don't know how many flights she has to look at until she finds 10 that aren't on time. So that is not going to be binomial. And this one here, in a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females is recorded. This one is not binomial because the trials are not independent. So if someone is selected, then it kind of affects your overall universe and they cannot be selected again. Now there is a binomial probability distribution function. You'll notice that this is given this formula is given under the Chapter 6 formulas. So there's nothing wrong with using this. I also want to kind of walk you through how you might do some of this in my math lab. Here are some common phrases and math symbols. This can be found in your textbook as well. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. We want to say that in a random sample of 20 car-owning households, what's the probability that exactly have 5? Or that exactly 5 have 3 or more cars. So what we're doing is we're looking for a binomial percentage. So we know that we have something that's binomial. So if you click on second vars, that'll take you to your distribution. We're talking about on our graphing calculator if you have one. And what you're going to do is you're going to scroll down till you see binomial PDF. And then in order to enter this in, you always put the number in your sample first, which in our case is going to be 20. And then we put a comma, and then we put our probability, which in our case is 0.35. And then we have another comma, and then we put what we're interested in, which in this case is 5. And then we close our parenthesis. And what we do if we get that is actually 0.127199, which rounds to this 0.1272. Now the other option you have is to use this, and this you can plug into your calculator as well. It just takes a little extra time. It's no big deal though. This one, you can also use the binomial calculator. In this case, though, you're going to use binomial CDF, which stands for cumulative. So you would hit second distribution, and then you'd scroll down to where you have binomial CDF, and you'd put in the same thing. So you'd put 20 for your n, and then you'd put a comma, and then you put your your probability, which is 0.35, and then you'd put another comma, and then you'd put 3. Because we want the probability that less than 4. So less than 4 actually means less than or equal to 3. Then you close your parenthesis, and you get 0.044375, which rounds to 0.0444. And similarly, if we wanted more than, what we would do is we'd take 1 minus the value that we got previously. We have a couple of formulas for mean and standard deviation. It's important that you know how and when to use these. These are the means and the standard deviations for a binomial experiment. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a simple random sample, excuse me, of 400 car-owning households, determine the mean and standard deviation of car-owning households that will have 3 or more cars. So if we want the mean, all we have to do is take n, which is the number of households in our sample, which in our case is 400, and multiply it by p, which in our case is 0.35. So if we do that, we get 140. And then if you want your standard deviation, you take n times p times 1 minus p, and then you take the square root of that. And for that, you should get 9.54. And these formulas are also given under Chapter 6. So you would use these when you have some kind of binomial random variable. Okay, Chapter 7. This is the normal probability distribution. So the most important thing that you're going to be doing in this section is calculating z-scores and then looking them up on the table. So z-score is always calculated by taking x, which is what you're interested in, your data item, and subtracting your mean, and then dividing by your standard deviation. And then once you do that, you're always going to be looking it up on a table. So in this case, we have IQ scores. They can be modeled by a normal distribution with a mean of 100 and a standard deviation of 15. And then what we want to know is an individual whose IQ score is 120 is 1.33 standard deviations above the mean. We want to know maybe how we got that. Okay, so they tell us, but we want to actually support it with a calculation. So what you could do is you could calculate the z-score for this person who has an IQ of 120. So if you want to calculate z-score, you just take 120, which is what you're interested in, and then you subtract your mean, which is 100, and divide by 15, which is your standard deviation. And if you do that, you get 1.33. So that gives you the number of standard deviations above the mean. This can also be done using normal CDF on your graphing calculator. Now we want to take that 1.33 and you can either use your calculator, or the tables are also provided on the exam with your formula sheet. So what you would do if you wanted to look up 1.33, you'd look up 1.3 on the left-hand side, 0.03 on the top for this digit right here, and you'd find the intersection. It would be 0.9082. Now, if we wanted the people that were above this score, what we would do is we'd use our complement rule, which would tell us to take 1 minus our 0.9082, and we would get 0.0918. So there are a couple of types of problems you can have. The basic idea is if you're trying to find the area to the left of x, all you have to do is calculate a z-score and look it up on your table, and that's going to give you your answer. If you want an area to the right, though, you have to do one extra thing. You calculate your z-score, you look it up on your table, and then you subtract from 1. Or you can use technology. And then if you want the area between, what you have to do is you have to calculate 2 different z-scores, find the table value for each, and then subtract so that you end up with a positive answer. The other thing I want to talk about in this section is normal probability plots. Basically, what we do is we plot observed data versus the normal scores. Normal scores are just the expected z-scores that we would see if the distribution was normal. Now, you don't have to calculate these by hand, but here we have Old Faithful geysers erupting in California, and we want to know if they're normally distributed. So what we do is we look at this nice normal probability plots, and we hope that maybe it's normal. So when we look at it, what we notice is we see an issue because we have this red dot that are outside of our blue bands. So anytime you have a red dot that is outside of your blue bands, we cannot say that it's normal. So what we would say is that the random variable, which is the time between our eruptions, is actually not normal. We can also do something called the normal approximation to the binomial. And this, you always have to verify that something is true. So n times p times 1 minus p has to at least be 10. And then the mean is always going to be n times p, and then the standard deviation is going to be n times p times 1 minus p. So if you notice, those are actually just the same formulas that were listed under the chapter 6 stuff. So that's your same mean and your standard deviation for your binomial. If you want just an exact probability, what you need to do is you need to subtract 0.5 from your value and add 0.5 to your value, and then find the probability between those two things. These are not given on your formula sheet, so it's important that you memorize this. If you want probability less than, what you have to do is you have to add 0.5 and then look to the left. If you want probability greater than, then you subtract 0.5 and you look to the right. And if you want between, then basically what you do is you take your probability that x is greater than a minus 0.5 and the probability that b is less than 0.05, and then you do your z-scores just like you normally would. Okay, so here it says, according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. So we already worked with this scenario. It wants us to figure out if in a random sample of 400 car-owning households, what's the probability that fewer than 150 have 3 or more cars? So we need to calculate our mean and our standard deviation. So the mean is just going to be calculated as 400 times 0.35, and the standard deviation is going to be 400 times 0.35 times 1 minus 0.35, and then the square root of that, which is 9.54. The other thing that we need to make sure of is that n times p times 1 minus p is at least 10. In our case, n times p times 1 minus p is 91, so that's a non-issue. And then if we want the probability that x is less than 150, really that means that we want the probability that x is less than or equal to 149. If you remember, when we have binomial and we want to use the normal to approximate, if we have less than or equal to, then we actually have to add 0.5 to our value. So what we want is the probability that x is less than or equal to 149.5. So what we do for that is we calculate our z-score. So you have what you're interested in, which is 149.5, minus your mean, which is 140, and divided by your standard deviation, which is 9.54, and you get 0.8413. We're going to skip B and move on to chapter 8, just so I can make sure we talk about a couple of things in this chapter. So let's say that we want to describe the distribution of a sample mean. So let's say we have weights of pennies minted after 1982. They're approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. What we want to know is what is the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams. So what we need to do is we need to find our mean and our standard deviation. So the mean is going to be the same as the population mean. It's just going to be 2.46. But if we're talking about a sample, we have to calculate our standard deviation for our sample mean. So what we need to do is we need to take our population standard deviation, which is 0.02, and we need to divide by square root of n. So if we do that, we're going to get 0.0063. Once we do that, we need to calculate a z-score just like we normally would. So we take what we're interested in, which is 2.465, we subtract our mean, and we divide by our new standard deviation that we calculated, and you get 0.79. Now we always want to look that up in the table, but since we want greater than, we do 1 minus our table value. So you get 1 minus 0.7852, which gives you 0.2148. Okay, a couple of other key points is that the mean of the sampling distribution is equal to the mean of the parent population, which we just used, and that the standard deviation of the sampling distribution of the sample mean is always going to be sigma over square root of n, regardless of the sample size. But one thing I want to talk about is the central limit theorem. And this basically tells you that the shape of your distribution for your sample mean becomes approximately normal as sample size n increases, regardless of the shape of the population. And typically what we want to have happen is we want at least 30 observations in order to use the central limit theorem. So let's do this one here. Let's suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes, and the standard deviation is 3.2 minutes. So we have a random sample of n equals 35 oil changes. We want to describe the sampling distribution. So we know that it's approximately normal because we can use central limit theorem. The mean is going to be 11.4, and the standard deviation is going to be 3.2 divided by square root of n. So in our case, that's going to be 0.5409. And then we want to know that if in a random sample of 35 oil changes, what's the probability that we get an oil change time average that is less than 11 minutes. So in order to do this, we just calculate our z-score. It's going to be what we're interested in, which is our 11 minutes, minus our mean, which is 11.4, and divided by that standard deviation that we calculated. And so if you do that, you get negative 0.74. And then we just look it up on the table, and we get 0.23. So here's a nice little summary. Basically, if you have a normal population, then your mean is just going to be mu, and your standard deviation is going to be sigma over square root of n. Another word for this is the margin of error for your sample mean. If you have a population that's not normal, then it's also going to be normal as long as you have enough observations, which normally we can say around 30 is a good benchmark. Your mean is going to just be the population mean, and then again, your sample error for your mean is calculated the same way. It's just sigma over square root of n. Okay, so let's do kind of one last example that walks through some proportion stuff from Chapter 8. So according to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-aged children aged 6 to 11, what's the probability that at least 19 are overweight? So if we want to figure this out, we need a couple of things to be true. So we need independence, which means that we can't have more than 5% of our sample size. N equals 90 is definitely going to be less than 5% of our population, so that is fine. In addition to that, n times p times 1 minus p has to at least be 10. So in this case, it's 13.7, which is good. So what we can say is that p hat is approximately normal. The mean is going to be 0.188, which is just given, and then the standard deviation we calculate as p times 1 minus p over n. And then we take the square root of that. And that's given on your formula sheet as well. So you take your 0.188, multiply by 1 minus 0.188, divide by 90, and then take square root. And then if we want to know what's the probability that at least 19% are overweight, what we do is we calculate z-score again. So we take 0.19, which is what you're interested in, subtract your mean, divide by your standard deviation, and then since we want at least, that means we want 19% or more. So what we would do is we would take 1 minus our table value, so we would get 0.4801. Okay, now let's suppose that a random sample of 90 school-aged children is chosen and it results in 24 overweight children. So what it says, what might you conclude? So for this one, we don't have our p hat, what we're interested in. So we need to calculate it. So in order to get that, we're going to take our 24 and divide by our 90 to get our p hat, which is our sample proportion. So we get 0.2667. And if we want to calculate z-score, we just take our value, subtract our mean, divide by our standard deviation, so we get 1.91. And then if we figure out a proportion for that, or percentage of observations that we would expect in that, it would just be 0.028. So it's very, very tiny. So we would only expect maybe 3 in 100 samples to result in a sample proportion that is 0.2667 or more. So we could say that it's unusual. Typically, we call things unusual if it's less than 5%. So that's it, guys. Good luck on your midterm, and feel free to email me if you have any questions on anything at all.